Okay, hi everyone. So hopefully by now you've done the stuff on satellite motion that I was talking about literally a minute ago, but now we're moving on to the second part of the fields topic, which is going to be on electric fields. And a lot of the concepts that we've covered as part of gravitational fields, they have analogous counterparts in electric fields. So just keep that in mind as we go through this topic. A lot of the things about electric field, they can be contrasted with the stuff that we've already done. Now, when we're talking about electric fields, we're saying electric fields are produced by objects with electric charge. They exert forces on other objects with electric charge. So when we talked about gravitational fields, we said that things can have mass. Anything with mass produces a gravitational field. Anything with mass is affected by another object's gravitational field. And it's analogous electric fields to that, because electric fields are produced by objects with electric charge. Objects with electric charge are affected by electric fields. There's some force exerted on charged objects by electric fields. Just like we were doing with gravitational fields, we can represent electric fields using field lines. There's a couple over here. I'll go over them in a bit. Gravitational field lines always pointed towards the object. When we had the picture of gravitational field lines from, I think, the second lesson that I filmed, you would have seen that the field lines were always pointing in towards the object. Electric field lines always point away from positive charges and towards negative charges. So this is something I've taken from your textbook. I think it's chapter 2.1. I could have checked. But we've got a positive charge and the field lines are pointing away in what we call a radial fashion. They're like spokes on a wheel, just pointed straight out. And because this is a positive charge, the arrows point away from the charge, showing the electric field lines. If this was a negative charge, the arrows would be pointed in. The pattern would be the same, but the arrows would be reversed. So that's just something to keep in mind with electric fields. They have a shape, and unlike gravitational fields, where the lines are always pointing in, because gravitational forces are always attractive, because we can have repulsive electric forces, not just attractive ones, we can have field lines pointing out or field lines pointing in. So that's another difference between gravitational forces and electric forces. Gravitational forces are always going to be two objects pulling towards each other. As you probably know, when we're talking about electric charges, opposite charges are going to, a positive, negative, are going to attract each other. We can also have repulsive forces, two positives, two negatives. We get that unlike how gravity works. When two charges are placed near each other, the electric field line pattern is a combination of the two patterns. So, like I said, I've got these in your textbook, from I believe 2.1. I'm just going to say 2.1 and I'll fix it up when a Teams post if I'm incorrect. Here I've got two charges. The field lines are going to move in towards the center, but they're going to basically be pushing away from each other. So here are my two charges. They want to repel each other. Their field lines are basically going to show the direction of a force on a positive charge. I thought I wrote that up somewhere, but apparently not. So say I was to put a positive charge on my first one up here. The positive charge is going to be pushed upwards. It's going to be pushed away from this positive charge in the middle. Wherever I put the positive charge, the direction of the arrow is going to show which direction the positive charge would be pushed. And on the other hand, if this was a negative charge, like I mentioned, the arrows would be pointing inwards. So if I had a negative charge in here and I put a positive charge out here, that positive charge would be pulled in towards the negative charge since they're attracted to each other. So you're going to get your arrows pointed inwards on the negative charge because the force on a positive charge would be towards that. So what was I talking about? So if I was to put a positive charge here, it would get pushed along the field lines. That would be the direction of the force on it. If it's right in the middle, this one's pushing the positive charge away, this one's pushing the positive charge that way. So the two forces along the middle are going to exactly balance each other out in the horizontal direction. If a positive charge would be put there, there'd be a force pushing it to the left and the force pushing it to the right, and the overall force would balance out. So the positive charge would remain in the middle. The lines go up, they basically asymptote towards a line that's just not on your diagram in the middle. So these lines don't end up touching, they just kind of end up moving kind of closer and closer towards the line that divides them. So this is two positive charges. By contrast, I've got a positive charge and a negative charge here. In between, the field lines are going to join up. There's a single straight line going from the positive charge towards the negative charge, and that's convenient because the arrows point away from the positive charge. They all join in and go to the negative charge, and they just curve in this kind of fashion around the middle there. There are some lines out here that basically go off and then it cuts off the edge of the picture, and there are lines coming in from outside the picture and connecting up to the negative charge. Just keep in mind that if there's a line, say this one, that line is basically just going to go around and then connect up with the corresponding line on the other side. So these lines are continuous. It's just that eventually you've got to choose where to stop and cut off the picture. Eventually there'd be lines going all the way down there, and you don't want to include those. So these lines, even though they're cut off, you should assume that they form a continuous loop around to the other side and connect up with the ones going into the negative charge. So just keep that in mind. Also, if we had this diagram, but instead of positive, positive, we had negative, negative, this picture would be exactly the same, except that instead of going out, the lines would be going in towards the negative charges. So exact same structure, just the arrows flipped the opposite direction. And the last one I've got on here is one that we're going to be looking at quite a bit. You've got two charged plates. One plate is positive overall, the other plate is negative overall. This is the structure of a capacitor. There's more stuff in a capacitor than is shown here, but we simplify it and say positive plate, negative plate, so positives along there and negatives along the bottom. We get an electric field in between these two that points from the positive towards the negative, the way you'd expect. We draw the field lines going from positive to negative, and the usefulness of this setup is that if we have this sort of deal, there's a bit of a bulge towards the outside. It gets more pronounced as you move towards the outside, just due to the fact that these plates aren't infinitely long, and eventually there's some kind of curvy effect because of the charges being near the ends. But in the middle, what we've got is an electric field strength that is essentially constant from point to point. So if the electric field strength, the strength of the electric field, something I'm going to go into next, is at a certain value here, then the electric field strength at every point inside is going to be at that same value. So this is a very useful setup when we're talking about electric fields, because we can talk about say an electron moving from one point in the field to a different point in the field without the electric field strength changing. So if we were talking about there's an electron here and it moves away from the proton, if there was an electron, it would move towards, as the electron moves, it's going to be moving to an area of a different electric field strength. We'll be calculating electric field strength in a future lesson, I think like the next one I'm going to record. But just know for now that it can vary from point to point, like when you've got a single charge, or it can be uniform, be the same from point to point, the electric field strength, when you've got this kind of parallel plates capacitor setup. So just something to keep in mind. That's why we like these setups, and you see them quite a bit, because you can assume a constant electric field strength as an object is moving through the field. Now let's see. Now, when we're talking about electric field strengths, we're talking about electric fields, we're talking about charged objects. So we're going to talk about the charge of an object, and we use the symbol little q to denote the charge of an object. It's going to have units of coulombs. So hopefully you've seen those before, but if not, well, it's just a unit that we use to designate how much charge something has. Electric field strength, big E, tells us how strong an electric field is, and it has units of newtons per coulomb. And if an object of charge q is at a location where the electric field strength is E, the electric force on the object is F equals the charge q times the electric field strength E. It's generally bad protocol to read to a PowerPoint, but at the same time, I'm not sure how legible these notes are going to be. So I just want to make sure that you understand what I'm referring to. And so I'm just reading them, whatever. So basic example is, what is the magnitude of the force on an object of charge 3 coulombs when it is in an electric field of strength 10 newtons per coulomb? And it's a simple calculation. The force on it is going to be its charge of 3 coulombs times the electric field strength of 10 newtons per coulomb. 3 times 10 gets me 30 newtons, force being in newtons. Shouldn't need to really explain that one by now. Now I do... have a think. Anyway, whatever. So like I was saying, we look at separated positive and negative plates a lot when we do electric field strength stuff, because the electric field strength is a constant in between them. If we've got these two separated plates, there is a potential difference between them. Potential difference is just a synonym, the same as voltage. So there's a voltage V between those plates. You've got separated charges. There's some potential energy associated with taking two charges that want to pull each other in, but are held apart. So there's some potential energy because these plates are held apart. That's what a potential difference is. And that's something that you're going to get between these two parallel plates. Second point about electric field strength between them is exactly the same. Yep. And I've got this equation that relates the electric field strength produced between these plates to the voltage V between the plates and the distance D of how far the plates are separated from each other. So electric field strength, just the voltage divided by the plate separation. Again, voltage is in volts. Distance has to be in standard units of meters, and generally when you have two parallel plates, they're going to be closer than a meter together. That's just normal stuff. You don't have capacitors that are that big that I know of. But yeah, you just use that calculation to get electric field strength, and I think that's what I do on the very next slide. I've been busy writing PowerPoints for the next set this morning, and my head's a bit muddled. So when a charge of Q is moved through a potential difference of V, the work done on its... I skipped over the calculation example. That's weird. Oh, I'm not going to reset the video. Whatever. So when a charge of Q is moved through a potential difference of V between the two plates, like the ones I've got here, the work done on it, the change in its energy, is going to be the voltage that it moves through times the charge of the object. So, for example, the question is asking how much energy would an electron, which has a charge of 1.6 or minus 1.6 times 10 to the negative 19 coulombs, need to move through a potential difference of 10 volts from the positive plate to the negative plate. So to unpack that, you've got an electron. It's hugging this plate. It's real happy being up there because it's attracted to the positive charges, repelled by the negative charges. It wants to be up there. It says how much energy would the electron need in order to be pulled down to this negative plate. We want to force it away from up here down to there. That's a distance, well, a voltage of 10 volts. I just took this picture from the last slide and updated it with information from the new question. There's nothing on here about electric field strength or distance of the plates. That's not information that I need, but I just didn't want to find a new picture I'd like to this one. So I just drew an electron on it and called that it a day. So I want to calculate the work that needs to be done, the energy that needs to be given to this electron in order to remove it down to here. And I just do that using my work equals voltage times the charge of the electron equation. So electrons have negative charge. The charge of an electron is a standard number. It's one of those numbers that you should get on your formula sheet. It's also a number that is very handy to remember because it pops up all the time, and people often confuse people confuse the charge of an electron with its mass in terms of the numbers. This is just a number that's going to be used over and over throughout year 12 physics, so it's just a good number to know off the top of your head. It's negative because electrons have negative charge. If this was a question about a proton, the calculations would be precisely the same. The proton would obviously have to be down there for this question to be the same question, but it would just have a positive charge instead. So protons, positive charge, 1.6 times 10 to the negative 19 coulombs. Just keep that in mind, something that's good to know. But when I do my calculation, I'm thinking of how much energy I need to give it. I know that I'm going to want a positive answer out, so I'm just going to use 1.6 rather than negative 1.6. It's not going to change anything. I just take my charge, which is Q. I kind of flip these here. My charge is Q and my voltage is 10. So I multiply those two things together and I get out that work of 1.6 times 10 to the negative 18 joules needs to be done on the electron to get it from up there to down there. So that's a question along those lines. Now the next question, which is, I really like this one, it's trickier, there's more to it. but it's essentially starting out exactly the same. See if I can budge the screen over to be like that. Yep, but then it moves right back. What do you know? It says, example 2, an electron which has a charge of exactly the same, it's an electron, and the mass of this, now I've thrown in the mass because that's something that you're going to need, starts at rest and moves through a potential difference of 10 volts towards the positive plate. So last example was up here and being forced down there. Now it's down here, and as soon as you let go of it, as soon as there's no force holding it in place, it's going to shoot up to the top plate, being attracted to the positive plate and repelled by the negative plate. The first question is, how much energy does it gain in moving from down there to up there? Exactly the same calculation as I did before. The work that's done is going to be 1.6 times 10 to the negative 19, the charge, times the voltage, 10. Same numbers because it's the same scenario. It's going to gain that energy in moving from down there to up there, whereas before it needed energy to remove it from the bottom top plate to the bottom plate. So things are operating in reverse just because the electron's in the opposite position to start out with. So same calculation, it gets that much energy when it moves from down there to up there. Now the second question is, what is its speed when it reaches the positive plate? Now to calculate that, I'm just going to say that it's got this much energy, assuming it starts from rest, which it tells you it does. It's got this much energy by the time it reaches the positive plate. That energy is going to take the form of kinetic energy. So all this energy that it's gained in its movement, it's going to have as kinetic energy. So I know its kinetic energy is 1.6 times 10 to the negative 18 joules. The equation for kinetic energy is just going to be half mv squared. I like to write 0.5 mv squared because it's easier to put into a calculator and also a PowerPoint. But I rearrange that equation, v equals the square root of 2ek over m, plug in my numbers, my my kinetic energy and my mass, and I get out 1.9 times 10 to the 6 meters per second. Now, in theory, because this is a classical equation, you could end up with a speed that's greater than the speed of light, but normally questions are going to be structured so that that doesn't happen. So because this is classical physics and it's not taking into account the relativistic stuff that we were doing last term, you could in theory get an answer greater than the speed of light doing this kind of calculation. So I'm just saying, like, if you get an answer like that, don't be concerned that something's gone wrong. Realistically, something probably has gone wrong because the question wouldn't be structured so that you get an answer like that. But I'm just saying it's possible that you could get an answer like that and that it would be consistent with the physics that is here. So just keep that in mind. It's always good to check your answer and make sure that it is a reasonable answer. But if it comes out unreasonably, then that could just be a byproduct of using classical physics and ignoring relativistic effects. So was that it? That's the question. That was it. Okay. So you should be now doing the questions from chapter 2.1 and doing the Ed Rollo questions related to electric fields. If you go into Ed Rollo, I'm sure you'll be able to see exactly which questions those are. Cool.